Hello, good day to you, and you're once again welcome to MES on Construction. So, we'll discuss all things engineering, architecture, and 3D modeling. Today, we'll be learning in Protastructure how to design your foundations, and we'll be actually designing a pad foundation in this tutorial for today. Now, to design your pad foundation, you need to have done your structural analysis. You need to have designed all the components of your structural element, and in order to do that you need to also make sure that you are on your story 0. And when you click on story 0, as we have done right now, you realize that you can no longer use your columns, your walls. You can use beams, you can use slabs, because in case you are designing something like a raft foundation or a beam raft or a slab raft, you need this too. But notwithstanding, what we need to do now is we are on our story 0. Then we can actually go down here and insert a pad and pad base. You also have the option of strip here, strip footing here, but we are not going to be doing that today. So what we're going to be doing is we're going to be inserting a pad foundation right here. We're going to be inserting a pad foundation, and you can't do that in your 3D mode. You can see that as I'm clicking it, it's not going. So you need to do that in your plan. And when you come back to your plan now, then you go to your story 0 for the plan, and you see that you have your columns right here. And here you can actually try to insert your pad foundation. So you can insert your pad base, by going here or just straight up going here to insert your pad footings. Now what we need to do is we have all these columns here, and then we already evaluated the load that each column is bearing, and we have a temporary spring that imitates the behavior of the foundation, but we still need to design the foundation itself to know exactly what we are working with. But before all else, you need the properties of the soil to design your foundation. And if you are designing a pad foundation, you don't just design pad foundation based on the fact that you just want to design a foundation. You design pad foundation based on the recommendation of your soil test or the nature of the soil in the area where the project is going to be executed. But it's always more advisable to design based on the reports of the soil test. And while in this climate in Nigeria and most places in Nigeria, we usually have pad foundation being sufficient for our structures because we have some good gravel soil, and we have a lot of good soils that can withstand the load that you are putting on top of it. Basic structures like duplexes and bungalows, and sometimes even story buildings that are not too high. You can design pad foundation for that if the bearing capacity of the soil is very good. So this project assumes that we are dealing with a soil with very good bearing capacity, and you can go here before you do anything else. You can go here to adjust the properties of your soil. You can do that by going here and go to foundations. And when you go to foundations, you see your parameters here, the soil unit weight. So this is just the default. That's the thin kilonewton parameter cube. And reliable stress 1.4. And reliable stress of soil is 200 kilonewton per meter square. And then the soil Pascals of gradient coefficient. So you have all these parameters here. And when you have this 200 kilonewton per meter square for reliable stress of soil, it shows that the soil is actually good. Like the soil is good and the soil is okay for pad foundation. If you design pad foundation based on this, you're going to have your foundation being sufficient for your drawings. And I think it also goes all the way down to around 80 kilonewton per meter square. You can still design pad foundation, even though at that level you might be requiring something like a wide strip pad foundation and all that, but I think it goes all the way down to 80 kilonewton per meter square, and anything below that you have to consider using raft foundation. If the soil test recommendation says 120 kilonewton per meter square requires a raft foundation, then you have to go with that. The soil test report supersedes every other authority the design of your foundation. So please just try to get that. Let's assume that this is just let's give it 120. Let's give it 120 kilonewton per meter square. Let's say we are assuming for the worst condition, for one of the worst condition. The worst condition is usually lower than this, but let's assume this is 120 kilonewton per meter squared. Then we can go to press OK. We can leave every other thing here. These are just the parameters of the pad foundation, the pad base minimum steel ratio, strip footing. And this is also very important, the minimum footing width. And the wider your footing, the stronger it is. Not necessarily like stronger like that, but what it does mean is that the pressure that will be acting on a point on the surface will be more well distributed when you have a wider surface than when you have a smaller surface. Because the job of the footing is actually to distribute the load that is coming from your columns to the soil. So this is why this is the default that's recommended, but you can also adjust it. You can make it 1-2. It's not really very advisable to reduce this. Also, the minimum pad base depth is 400. This is the depth of your pad foundation. It means that from the point of excavation of your foundation floor, you need to excavate your column depth to be around 400. And after you excavated this 400, then you now put your basket. We call it basket here, which is the pad base, the reinforcement for the pad base. You put it at the depth of 400. Then maximum steel bar spacing is actually the steel bar spacing that you have between your reinforcement bars constituting the basket. Maximum steel bar spacing. Some people usually manipulate this, but I won't advise it. I think it's just very okay like this. Then you have the size increment step. This, if one particular size is not sufficient, the increment step is automatically by 100, and the depth increment for the size is also 100. And you have the pad bases, concrete cover for the pad bases to be 40 millimeters. And I think this 40 is okay. You decide to increase or decrease it as structural engineer, depending on what you believe you are designing and what is good for you. The minimum steel bar size Y16, the distribution bar Y16. You can actually reduce this, but here we are not going to be reducing it here. You can see that we don't have the option, we don't even have the luxury to do that. So we don't want to use top bars. There are some instances where you need to use top bars on your foundation reinforcement, which means you have a basket as in the bottom bar, you also have a basket as the top bar. For this design, I don't think it's necessary for us to use both top and bottom bars. When you have top bars, it actually helps also against the hugging moment, where you have a lot of stress coming upon your structural member, upon your columns, and you're putting a lot of stress. So now we can press OK, and you can go ahead to just click on your columns and then insert pad footing. And once you press that, it takes a little bit of time to load. Before it inserts the pad footing, it comes up with these settings, and you can see from our settings we have the label for the column that we just clicked, and the depth, just like we discussed, 400. The tapered height, we are not tapering the column, it's not a tapered column, so we don't need a taper height. And concrete cover, just like we said initially, is 40 mm. Then you have the LX. This is the length along the x-axis. The length along the x-axis. This is the length along the y-axis. The length along the x-axis, you can see it's given like this. Length along the y-axis is given like this. And when you look at this, it tells us that the design is successful. The net bearing capacity is 168, which is greater than 165. So you can see that at the end of the day, what your pad does is that it helps you to distribute the load effectively on the soil in a way that the soil bearing capacity is able to withstand the load that is coming upon it. And here you can see that 168 is the soil stress net bearing capacity of the soil, which is now greater than what is coming on top of it, which is 165.84, and it says this is okay. So when you look at this, the margin is so small that if you remove any of this, like you remove this one, you turn it to 1100, you see that it immediately turns red. This design has failed. You can design for a little bit of symmetry so that there won't be mental gymnastics on those that are executing your project. especially if you're not the one executing your project. And that's why sometimes you often see designs like a basket has the same length across the x-axis and the same width along the y-axis. And that's actually really for symmetry and for ease of transferability. Sometimes it's designed like that. Before design, let's go to 3D to visualize what it looks like. And you can see now you have this like this, you have this like this. You're still going to go and touch and you're still going to go and touch the design. So you have your column, then you have your basket right here. So when you count this basket now, you see that we have in this basket you have 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 9 y. I don't know whether it's y16 or y12, but we're going to touch that 1, 2, 3, 4, 5, 6, 7, 8, 9 because we have the same length, the same length across the x and y axis is likely going to be the same reinforcement numbers, same number of bars going through. So you have this red as the main bar, then you have the yellow as the distribution bar. And the main bar is usually the bar along the shorter span, while the distribution bar is usually the one along the longer span. But here you don't really have anyone along. There's no shorter span, there's no longer span, which means anyone can be top and bottom here. So now you also have the load distribution factors here across each point. So that across this point is 152, across this point is 109, across this point is 77, across this point it is 109. So you have that. Now let's go and look at the rebars. So you see that you have the rebar along the x-axis. So it's y16 we are using. You can turn this y16 down to 12, but I don't think we can do it here also. We can go back to our analysis and all that and manipulate this and change it because we've already set the default to 16. So if you want to change this to 12, we have to go and adjust it right there. So and we have the spacing to be 150. I don't need distribution bars here. This is sufficient for us, and you can see that even here it says that design is successful. We don't need that for now. For this design we don't need it. So let's go to the material is using for us. You see the concrete grade is 1620, the rebar is grade 410, the ultimate stress of the soil that's 168 kilonewton per meter square, then soil unit is 18,000 kilonewton per meter square. So now field height now is 700, then net bearing capacity is 155.4, and ultimate strength factor is 1.4. So let's just press OK, and you see that our pad foundation now is designed. And when you go to your 3D, you see pad right here. So now we have changed our reinforcement to y12, and from here you see that we have 9y12 and then in the x-axis, and we have 9y12 running in the y-axis. And if you go to your 3D, you see that it's shown like this. It's shown like this. You have 9y12 here, and you have 9y12 also running for your basket there. Then your column is naturally y16, and you have that about that. And you can see here too, these are the load distributions. You can see the load distributions here at each point. And you also have the depth of the, I think I adjusted this to 500. I'm turning it down to 400 and it'll still be okay. So, and I think I mistakenly just touched it. So it's 400, and you can see that everything design is successful. So you still have your load here, and at this point you have this 119, which is this, and 9 for the 75 here, and you have your depth to 400. So this is what you're excavating further from your foundation excavation floor to have your column base reinforcement. And now we can go on to press OK. And once you press OK, you see that we have our design status here, and this design status doesn't just work for everything that's done so far, it also works for the foundation. And here you can see that it says it's painted green, which means that this part foundation right here is okay. And then you can go back to our story 0 and create for other foundations. But then you can also do something fantastical by just selecting everything all at once, and then we design all of them all at once. Okay, then we can select this, then we can go on and create insert part fitting for everything at once. And you see, it brings us this and it designs everything just like that. And then we can go into each and every one of them to check what parameters are adhering, especially when you realize that the parameters you're having are not really quite giving you what you want. It's always good for you to go inside and edit yourself. So we have these ones to be this F17 to be 1800 by 1100. When we come here to check the soil stress net bearing capacity, you see that this is 168, which is greater than 161, and this is quite close. If we reduce this by 1/8, that's failing. So it means that we can't actually do that. So for symmetry, we can go with 1/9. Because most of the time when you're designing for economy, you want to make sure that you have everything settled. So I'm just going to leave it at 1900 because, and this satisfies the fact that the wider your base, the more efficient it's able to transfer load coming from the column to the foundation. And you can go on to press OK. As you can see, it's giving us 14Y12 at 150. So you have the top and you have the bottom, and you can go to view the 3D and you see what exactly we're talking about. So this is 1900 by 1900. That's just all about that. Here also, everything is designed. You can check this. You have 1000. You can change this to 1200 by 1200. This 164 is also very close. Check your bars and remove this. Then you can also go to this and you can also edit through this, instead of just going there and realize that your design is actually okay, instead of you going into your design to check. But one of the reasons why I prefer to go into the design to check really is because I want to really know what's really going on. So but you can actually edit from here and it's still very fine. You can edit from here. It's very, very fine. This is 1 4 by 1, 1 2 by 1 2. And you see that if you reduce this, it's going to tell you that it's not sufficient. Now you see that it tells you that it's not sufficient. And it's also the same thing to tell you if you go inside. So you can actually adjust that. And once you do, see that it's sufficient right here. So you can have this 1 2 to be 1 2 by 1 2. This symmetry helps to, make it easier when you are trying to interpret your design, because when you have too many different column based types, it leaves room for confusion, especially in complex designs. It leaves room for confusion. So it's not just about you just creating something that is stable and economic, also creating something that is transferable, that you consider the fact that there are people that are actually going to be transferring this drawing into reality, and they need to be able to have an ease of understanding what you're doing. More like you're writing and someone else has to read what you're writing. Your writing has to be as clear as possible to help them to understand what they are reading. So you can press OK and you see that it designs everything right away, and you have all our column bases here. You can edit in your Protadetails, and from your Protadetails you could export as DXF into AutoCAD, and in AutoCAD you'll be able to classify each column into the type of base based on their size and for ease of transferability also. And I think this is just about enough for all we have for today on part foundation design. I hope you're able to learn a thing or two. In our next lesson, we will try to touch on how to work on your Protadetails and transfer your columns from Protadetails also into AutoCAD. Don't forget to subscribe to our channel for more content like this. Hit the notification bell to be the first to see our latest video tutorials on Protastructure. Thanks for watching and bye for now.